So, good morning, everybody. We start the first talk with Danny Phillips, who will tell us about the spectral evolution of hybrid white dwarfs.
Thank you, Nicole. Good morning, everyone. I'm Semih. I'm about to finish my PhD under the supervision of Klaus Werner and Thomas Rah at the University of Tübingen, but at the moment I'm working with Nicole Reindl at the Heidelberg Observatory. In this project, we also collaborated with Dave Jones, Paulina Sowiska, and Matthew Dorsch. Today, I will talk about spectral evolution of hot hybrid white dwarfs. And in this project, in this sample, we also have 9 central stars. So I think some of the results might be also interesting for you. So the evolution of the central stars can be divided into 2 major channels: hydrogen-rich channel and the helium-rich channel. Today we will be focusing on hydrogen-rich channel, and this is a simple sequence that is shown here. Hydrogen-rich central star evolves into DAO white dwarf or hybrid white dwarfs, which can be distinguished by the helium-2 4686 line in the optical spectrum, and then it evolves to hydrogen-rich white dwarf. This is a simple picture expected by the theory. But then when we see the observations, here the red squares represent the DA white dwarfs and blue dots represent the DAO hybrid white dwarfs, and the central stars are marked with purple octagons. So what we would expect, according to theory, below this dashed line, the helium abundance should have dropped to 10 to the minus 3. Why do I not use this? So the helium abundance should have dropped 10 to the minus 3 below this region. But as we can see, that DAO and DA white dwarfs, hybrid and hydrogen-rich white dwarfs, reside in the same region. So why this is the case? Is there anything wrong with the theory? Is there anything wrong with the observations? Or is there something that we don't know? So, but for that reason, because, sorry, in order to shed light on these questions, we need to determine our atmospheric parameters as much as we can. But as many of you might know, that the analysis of hot hydrogen-rich white dwarfs are heavily hampered by the so-called Balmer line problem, which can be described as the inability to fit all Balmer lines at the same time with the same TF and log G. So for that reason, if we have UV spectrum as well, we can measure TF and log G much better, more precise, with in addition to optical spectra, and we can only get metal abundances from UV. So for that reason, we selected a sample of hot white dwarfs, hot hydrogen-rich white dwarfs, in which there were 9 central stars. These objects are above 60,000 Kelvin with archival UV and optical spectra. So we would like to measure the stellar parameters and the abundances by exploiting metal lines in the UV, and as well as radii, masses, and luminosities. We want to know whether there is a well-defined wind limit exists and we would like to compare central star abundances to planetary nebula abundances. And we also would like to know how the spectroscopic distance compared to Gaia distances. So the first part of my talk, spectral analysis, we use TMAP to calculate non-LTE plane parallel chemically homogeneous models in hydrostatic and radiative equilibrium. And in each model contains this, all of these elements written below, which is actually quite computationally expensive. So here I show an example plot from Fuse Spectra, one of the hybrid white dwarfs. Red lines represent our photospheric TMAP model, and blue lines represent the interstellar lines. We used multiple ionization equilibria such as carbon 4, carbon 3, oxygen 5, oxygen 4, oxygen 6, or iron 6, iron 7 to constrain effective temperature. But what I mean by the ionization equilibria, here, two of the central stars, one of them in the HST region and the other one is in the Fuse region. So if I fit all of these iron 5, iron 6 ions with the same temperature and log G, and if I have like multiple ions like that, carbon 3, carbon 4, or whatever, according to temperature, then I have a very good estimate for my temperature. And for log G, here you saw that the ISM lines heavily dominate the UV spectrum. Therefore, we also need optical spectra to constrain log G tightly. So now our results. In the beginning of my talk, I told that there was a mixture in the TF and log G diagram. But after our analysis with optical and UV, we see that DAO and DA white dwarfs are clearly separated in the TF log G diagram, which is what is expected from the theory. So what would be interesting for you is that we compared planetary nebula abundances to central star abundances. Central stars are shown with the star symbols, and for the planetary nebula abundances, we have the circles. For most of the objects, for only 5 objects, we could find planetary nebula abundances, and in general, most of them fit quite well. Other than here, for one of the objects, we have slight disagreement with the iron abundance, and here a slight disagreement with the sulfur. But in general, we have a very good agreement between the abundances from planetary nebula and the central star. So this topic has been going on since Monday, the comparison of post-AGB cooling ages and the kinematical ages. What we did is to calculate, actually measure the post-AGB ages from Marcellus tracks, and then from the literature, Gonzalez Santamaria, the kinematic ages. And then as we see that generally post-AGB ages, cooling ages are higher than the kinematic ages. And this actually tells us if we infer effective temperature or like any central star parameters from the kinematic ages of the planetary nebula by going back to the post-AGB cooling ages, there might be some errors while getting the central star parameters. So I would take those results with a grain of salt. And the second part of my talk is about photometry. So we conducted a photometric analysis to search for photometric variability, and in our sample, 13% of our objects are photometrically variable, and this is in agreement what is reported by previous studies. for hot hydrogen-rich white dwarfs. And however, we didn't find any photometrically variable for central stars. This was also in Nichols 2024 paper. There were like 17 hydrogen-rich central stars, and she also didn't find any photometrically variable objects. Then we performed fits to spectral energy distributions to calculate radii, gravity masses, luminosities, and distances. And we fixed effective temperature and log G from the spectral analysis, and from the only the reddening color excess and the angular diameter remained as free parameters. Then we performed, if there is any infrared excess, we performed a multi-component fit, and using the Phoenix grids in this, so we found only one central stars with infrared excess, and just 1 out of 9 objects. So this is VDES 0851. The companion parameters from our SED fit is written here, and this is in agreement with the previously found results. And the system is not resolved by Gaia, but it was previously resolved by HST. And with the updated Gaia parallaxes, we calculated the separation of 140 AU, which means that this is a wide non-interacting binary. And in the second part, we calculated spectroscopic distances. We have the angular diameter from the SED and log G from spectroscopy. And for the mass, we interpolated from the evolutionary tracks and calculated the spectroscopic distance. Then we compared this to Gaia parallax distances. However, what we find that there is a slight disagreement. Actually, this is a known problem for hot pure white dwarfs and central stars of planetary nebula. And in almost in all cases, always parallax distances are smaller. So in our sample, we found 4 of 9 central stars show this distance disagreement, and we can't find a clear origin for this disagreement, but we suspect that this could be related to effective temperature. So my summary and conclusion, we performed a very homogeneous analysis with the same code and same atomic data, and this resulted in a full agreement between UV and optical spectra. And we found that DAO to DA transformation around 80,000 Kelvin. The helium abundances were really well predicted by the wind theories when we saw the separation in the TF log G diagram. We did not find any photometrically variable central stars. There is only one excess among the central stars, which is a white binary. We found that in general, there is a nice agreement between central stars and the planetary nebula balances, and there is a disagreement between spectroscopic distance and Gaia distances. So actually, our study shows that these objects are just boring canonical single stellar evolution objects. So if you're interested, you can check our paper from this QR code. Thank you very much.
Thank you, Sumi. Are there any questions?
Here's a short one. The infrared access, are you talking about near infrared access or mid infrared access?
Near infrared access.
So
Here,
it's really close to the central.
yeah, exactly. Here, you can see the access for these objects. And I mean, there's also not exactly meet, but like not near, I would say, the Weiss-Bahn and Weiss-2 bands. We see the excess, and yeah.
Is there any reason to think that plane parallel static atmospheres are not giving you sufficient precision? And there's a lot of very sophisticated abundance analysis connected to galactic archaeology. Of course, there are different types of stars that don't apply to light works.
So as you know, white dwarfs have like very small atmospheres compared to their core, but which I try to show here. So the this is the atmosphere compared to the white dwarf itself. So the plane parallel works very well.
I mean, it's a lot of meditation and.
Yeah, exactly. So for that, actually, one of the main also, so we also looked the abundances in the TF log G diagram. So if you go to like this region, then the diffusion starts to be very effective. We see that from the iron and nickel lines, iron and nickel abundances. And around this region, actually, the radiative levitation starts to be very important. And like above this, for the central star region, we generally don't think this would be a problem. Because we predict, I mean, not we, a big mass loss is predicted for these objects, and this homogenizes the atmosphere, so that also works.
Thank you for the presentation.
Thank you.
So this is a bit more connected to the conclusion than to the work itself, but you find that these things more or less agree with, let's say, canonical single-star evolution. Some of them are like central star supply time comparison. So when do the planetary nebulae around them, how do they look like? I mean, do they look like, are they especially symmetric, or do they look like with all those shapes and morphology that you see in the other ones? Because this is something I'm particularly.
To be honest, I was never interested in that, so I didn't. As Nicole said yesterday, most of the time planetary nebula is tiny bit annoyance for us. So I don't know, like I can't comment on that, sorry.
That was it. Because I think it would be interesting once that you have more or less concluded that because of the abundances of the planetary nebulae, the central stars, that they always come from a single star, to check whether that has some connection to the shapes of the planetary nebulae around.
Yeah, that's true.
One more question.
Yeah, Nicole.
A quick comment. I know you are not interested in morphology, but there is a beautiful image of Abel 31 in poster 48 by Faisal.
Okay.
Okay, so
I will.
So you can enjoy the image there.
I will definitely check that.
Okay, but I have a question. Why could you expect the same chemical abundances in the planetary nebulae of the central star?
So if we say that like this is the expelled, so before the planetary nebula expel its mass, we expect a certain abundance pattern, right? And when it expels, the abundance pattern will not change. This will be the surface abundance of the planetary nebula. So therefore, we might, I mean, some of the elements we see. I mean, this, if I correct, for elements like sulfur, we would definitely see the same abundance. But for carbon, maybe after the third dredge up, if there is third dredge up, we might
also the position into dust grains and also for ions. So this is going to change the abundances. I would also expect the abundances of the atmosphere to change if there is a variation of the position.
Yeah, that's true. But like that would be probably like as I showed in when the white dwarf cools down much more, then I think we would definitely see more differences.
Thank you.
Thank you.
Okay, let's thank Xenia again. And then we continue with Paulina Sovinka. And she will tell us if there's a link between pulsating PGL 59 stars and the morphology of the PN. And no photos must be taken during the talk, please.